Welcome to Hartman Math. Today we're going to take a look at logarithmic functions and their graphs. Section 3.2, definition of the logarithmic function. A couple conditions here. In our function y equals log base a of x. That's how we say it. Back to that. The x, whatever we're taking the log of, must be positive. Our base, like it was when we were talking about exponential functions, the base must be positive and the base cannot be 1. And this is true if and only if the exponential equation is true, x equals a to the power of y. So the function we read again, read as log base a of x. So after you say log, you say the word base, you say what the base is, and we say what we're taking the log of. That's the logarithmic function with base a. Example number 1, evaluating logarithmic functions. Log base 3 of 81. Around here we like to say a log is an exponent. So essentially what we would be doing here, we could evaluate this really without a whole lot of work, definitely not having to show anything. Looking at the base 3, so we'd say 3 to what power is 81? We should know that's 4. So we'll just write 4. The answer is 4. You don't need to write this stuff here. It's just the reasoning. The answer is 4. The answer is just going to be a number. Part B, log base 27 of 9. We may not know that one nearly as well if we say 27 to what power is 9. Kind of see in a moment how we might be able to reason through that, but definitely probably not right now. So if it's one that you don't know and we're expected to do this without a calculator, we're going to say equals and turn it into some equation. So it's equal to any variable that you would like it to be. So we'll just say equals k or x or capital B, whatever you want it to be. Then what we're going to do is we're going to rewrite this back into exponential form. And the way that we do that is we're going to move the base. We always move the base. So 9 will stay. 27 moves to the other side. Since it's the base over here, it will become the base over here as we're rewriting it as exponential. And since 27 is the base, that would bump up the k to be the exponent. And then we would want to try to equate the bases. So we need both sides to be equivalent bases. Both 9 and 27 are powers of 3, so we're going to rewrite both as powers of 3. 3 to the second, 3 to the third, which will be raised to the k. And then a little step we skipped here was when it was 3 to the third to the k. When you raise a power to a power, you just multiply the two exponents. Well, since the bases are the same, we can ignore them and say exponent equals exponent. So 2 equals 3k, and solve, and you get 2/3. Before we get to our checkpoint, so another way we can kind of go back to this, knowing that 27 and 9 both share a base of 3, how do we turn 27 into that 3? You would take the cube root. Well, cube root means an exponent. Remember, log's an exponent. Exponent of 1/3. 1/3. And then what would we do with that base of 3? We would square it. That's an exponent of 2. 1/3 times 2 is 2/3. All right, so checkpoint. See if you can go ahead and do evaluate. It's another way of looking at it. It's basically the same thing as example number 1, but we would, if we're doing f of 125, we'd just be doing log base 5 of 125 and evaluate. Pause the video here while you work through A, B, and C. First one, pretty easy one. 5 to what power is 125? Answer is 3. Second one, g of 1, so log base pi of 1. Pi to what power is 1? Well, that's just the zero exponent property. Any number raised to the 0 power is always going to be 1. And last one, this one's the one that's a little challenging. You might need to kind of write some work out on that one. That one turns out to be negative a half. The decimal is not really your friend here. You want to think of this as being a half. And then if we didn't know, set it log base 4 of 1/2 equals k, if we want to look at it like that. And then work it where you're trying to use both sides to be powers of 2. So you want to rewrite it so that it's an exponential equation and then solve for k from there. All right, some common logarithms or important logarithms as far as their bases. We've seen base 5, base pi, base 4. We saw initially that the base just had to be positive. Well, there are a couple special bases. And the first special base is base 10. That will be called the common logarithm. And the saying is, when we're doing log base 10, you actually don't have to write the base. If you just say log of x, that means log base 10 of x. So notice on your calculator, if you see the log button, that's log base 10. That's a common logarithm. So example 2, how to use the calculator in that. So all you have to do to evaluate, run around to the 1,000, 3 decimal places, is just type in log 75 equals round appropriately. And check and make sure you can get 1.875 or 1 and 875 thousandths. So some properties of logarithms. Log base anything of 1 will always be 0 as long as we have a legal base. Remember, our base has to be positive and cannot be 1. And that's due to the 0 exponent property. Log base anything of itself, as long as, again, we have a legal base, will always be 1 because a to what power is a, and that is the first power. One that you may not have kind of seen maybe in Math 3, the inverse properties, log base a of a to a power will always be that power. So the answer is the exponent, as essentially the log base a and the a to the power of are inverses and cancel each other out. And then conversely on that one, we also do that as exponent property, a to the power of log base a of x, again, just kind of cancel each other out, would be x. And then our one-to-one property, which we saw for exponential functions yesterday, is now, we can do it for logs. So log base a of x is equal to log base a of y. Again, as long as the a's are legit bases. Then our argument, that's called an argument. The arguments have to be equal. All right, example 3, use properties of logarithms to simplify. Part A, log base 9 of 1 is property number 1. Log base anything of 1 will always be 0. Part B, log base root 11 of root 11 is property number 2. Log base anything of itself will always be 1. And then part C, 8 to the power of log base 8 of 8. Since our bases are the same, those will essentially cancel out, and we're left with the 30. Property 3, one of our inverse properties. See if we can use the one-to-one property to solve a logarithmic equation. Notice that both sides are log base 3 of an argument equals log base 3 of an argument. So we are set up for the one-to-one property already, which says the two arguments have to be equal to each other. And then we can go ahead and solve that. So perhaps subtract 4 both sides. Take the square root on both sides. Don't forget that when we square root both sides of an equation, need a positive and negative answer. And then we do need to check with log equations, and we'll get back to this at a later time also. Because of the domain, our input having to be positive. We do need to check both answers. So if we try 5 squared is 25, plus 4 is 29. You can take log base 3 of 29. And negative 5, we also get 29, so both of them do work. We do need to check all log equations on our solutions. We'll box that answer, so both of those answers are fine. Graphing exponential and logarithmic functions. In lesson 3.1, we did graph f of x equals 2 to the power of x. We did that by doing f of 0, 2 to the 0 power is 1, plot a point. And then did f of 1, 2 to the first power is 2, plot a point. And we graphed that. It did have an asymptote. Which was the x-axis, y equals 0. And we had all the other information, domain, range, and y-intercept. Well, for g of x being log base 2 of x, that is the inverse to 2 to the power of x. And so we can use the idea of graphing inverses, which is back from chapter 1, where we reflect the graph in the diagonal line y equals x. We could also just switch the x and y coordinates. So 0, 1 now becomes 1, 0. Plot a point for g of x. And 1, 2 becomes 2, 1. And as far as a reflection goes, it then looks like this. So the domain, notice that everything is now to the right of the y-axis. The domain has to be positive x values, and therefore parentheses 0, infinity. The range goes forever down and forever up. So that's all real numbers, negative infinity to positive infinity. The x-intercept is 1, 0. The asymptote, as it goes down here, we keep getting closer and closer to the y-axis, which has the equation of x equals 0. So an important thing here with our inverses, notice the domain here is the range of the inverse, and vice versa. Now that we have that, we should be able to use this and not have to rely on graphing the exponential function every time we want to graph a log function. So if we're just graphing a log function, log base a of x, the two key points are 1, 0, base, 1. This is 2, 1 because the base is 2. If this had been log base 4, it would have been over here at 4, 1. So the 2 points are 1, 0, base, 1. Let's use that idea to do example number 6, where we have to sketch the graph of this. So first we want to graph the parent function, which is log base 3 of x. Stop at the x. That's where we're going to graph. So that's our base function. So as we just went over, 1, 0, base, 1. So 1, 0 and 3, 1 are the 2 points, and the base function will always get close to our asymptote, the y-axis. Now we have to perform any transformations, no stretching, no reflecting. We just have the shift here that is inside the function. So if it didn't have the parentheses, it would be a different shift. This is inside the function, which means it's going to be horizontal. Think opposite, right 1. So we're going to move everything right 1, and that does include the asymptote. So move the 2 points right 1, and then redraw the asymptote right 1 as well. So our new domain, after we've done the translation, the shifting, everything's right of 1. That's our domain. Range should not be affected. Still forever down, still forever up. X-intercept has shifted to 2, 0. The asymptote is now x equals 1. Notice there will be a connection between your asymptote and your domain. Checkpoint. Graph k of x. After you've graphed k of x, provide the domain, the range, the x-intercept, and the asymptote. Pause the video here. Our parent function is log base 2 of x. So we graph that, 1 comma 0, base comma 1, since our base is 2. No parentheses this time, so our translation, our shift is vertical, up 3 with all of our points. The domain has not changed, the range has not changed. The x-intercept is a little bit interesting. It's hitting here. We don't want to necessarily guess on that, so we should probably work that one out. So if we're thinking about it, go back to our equation and have it be equal to 0. Log base 2 of x plus 3 is equal to 0. So when is the y-coordinate 0? That's going to give us our x-intercept. And then let's solve for x. So let's get rid of the 3. Let's rewrite from log form to exponential form. Move the base. 2 stays as the base. Bumps up the negative 3 as the exponent. So we're looking at 2 to the negative 3rd power, which means 1 over 2 cubed, which is 1/8. And our asymptote should kind of correlate and match to the domain. The other of our special bases looked at in lesson 3.1, the natural base e. So that's the other special base here. F of x equals e to the power of x is the natural exponential function. And therefore, if we do that as the base, log base e of x, that's the natural logarithmic function. Except we don't typically write it like this. There's special notation. And it is ln of x. So that's ln, it's not capital I-N, it's ln. So you might notice on your calculator you have a button that says capital L, capital N. That's the natural log button. I do have a question for you. Ponder it for a second. You can pause the video here and think about it. My question is, if it's the natural logarithm or natural log, why is it ln? Think about that. Answer to that question comes from your world language class. Do you take Spanish? Do you take French? Both languages are Latin-based, and in those two languages, we put the adjective after the noun, or we don't do that in English. So, and this actually would be French here, it would be logarithm natural. So that's why it's ln and not nl. So ln of x is the natural log function. It is log base e. So to evaluate that, we do have the natural log button on your calculator. We can just type in the natural log ln button, square root 111. Let's again round to 3 decimal places. You should get 2.355. Make sure you can verify that you do get that. Properties of natural logarithms really shouldn't be much different. The natural log of 1, also 0 because of the 0 exponent property. The natural log of e is 1 because remember, natural log is log base e, so we're talking about e to what power is e. So that would be 1. And then as far as inverse properties, the natural log of e to the x, since it's log base e of e to a power, they cancel out. The answer is the exponent. You can also look at that kind of reversed in exponential form. And the 1-to-1 property gets similar. If it's natural log equals natural log, then the arguments have to be equal. Example number 9. Use the properties of natural logarithms. Simplify part A. Natural log of e to the 1/2 power takes us to here, where natural log and e cancel out. The answer is the exponent. E to the natural log of 8. Again, natural log is log base e. So e to the power, natural log cancel out. We're on this one. The answer is 8. And part C, the natural log of e over 6. Well, the natural log of e is 1. So we just get 1 over 6. We use property 2 for that one. That's it for today. I'll see you next time.